everybody. We're going to continue on with our study of Schroeder's Chapter 1 in thermodynamics and talk about gases and ideal gases, specifically their equation of state. This is going to be an introduction to that topic, and then a microscopic look at the ideal gas law will be done in a separate lecture. So first of all, let's discuss what equations of state do. So it's useful to know how these state variables like volume, pressure, and temperature and the mass relate to one another. Any kind of equation that relates quantities such as this is called an equation of state. Now, most equations of state are quite complicated. The ideal gas law is kind of the exception to that, and it's so useful that it's often taught in middle schools and high schools. The equation of state for an ideal gas, it's important to understand that there's certain restrictions on when you can use it, and it's important to understand that it is an approximation to the truth. So ideal gas laws, for example, work at low pressures of the gas, and in that case the equation of state for it is much more simple and applicable. If you get to high pressures and high densities of gas, it doesn't work anymore because the equation of state becomes much more complicated than the simple ideal gas law. Now, we use equations of state to predict behavior, and it's important to understand that the ideal gas law is just one of many equations of state. But like we said, it's a simple one, it's nice, people like it, so it gets taught a lot, and it does do pretty well at making a lot of predictions. Now, I mentioned some state variables. Equations of state relate state variables. We've already talked about some of these state variables like volume and pressure. There's also mass density, moles, number density, temperature, and other state variables that get used in thermodynamics. Let's delve a little bit more into some of the assumptions that underlie the ideal gas law. So one of the number one assumptions is that for ideal gases, the interatomic forces in that gas are really weak. In fact, we imagine them to be pretty much non-existent. Now, this is going to break down under certain conditions. For example, as nitrogen gas gets colder and colder and colder, and closer to the transition point for when it becomes a liquid at 77 Kelvin, then the ideal gas law starts to break down because those nitrogen molecules start to become more and more attracted to one another. There's some other gases out there that are chemically reactive with one another, for example, and the ideal gas law wouldn't hold very well for them either because there's an attraction between gas molecules. Now, it's also important to realize that an ideal gas assumption is that there's no equilibrium separation for the atoms. In fact, this is a nice assumption for gases in general. There's no standard volume at a given temperature because gases expand to fill the containers that they're in. As I already mentioned, ideal gas model works well at low pressures. Now, it's important to realize that what we experience as atmospheric pressure is actually a low pressure here. So we're really talking about pressurized gas containers and high pressures like that as to where the ideal gas law doesn't work so well anymore. Now, as we mentioned, for a gas, the volume is entirely determined by the container holding it. They don't have typical densities. This distinguishes them from solids, for example. So plastic, for example, has a typical density to it, and that means that the atoms are spaced at very set spacings. Equations involving gases will contain the volume, V, as a variable, and also the number of particles, N, as a variable. So you can calculate the density by taking N and dividing it by V, but this density will change a lot for different conditions, okay? That makes it different for something like lead. If you have lead and it's sitting there, you can heat it up, and until it melts, it'll only expand a little bit, and it'll still pretty much hold that same density. The same cannot be said for gases. Their volume expansion coefficients are through the roof compared to that for solids and liquids. Okay, so the ideal gas law that we know and love is actually a combination of other gas laws. So when a gas is kept at a constant temperature, its pressure is inversely proportional to its volume. This is known as Boyles Law. You might have seen this in some common physics demos where, for example, they took a balloon and put it inside a vacuum chamber and pumped it out. And you can see that as the pressure decreases inside the chamber, the balloon expands. Another gas law that is combined into the ideal gas law is that when a gas is kept at a constant pressure, its volume is directly proportional to its temperature. This demo is commonly done where you have a container of liquid nitrogen and you drop a balloon into the container of liquid nitrogen and the balloon shrinks down until it's this little flat pancake. So you might have seen that demo. Another gas law is when the volume of a gas is kept constant, the pressure is directly proportional to the temperature. A common application of this idea are pressure cookers. So we combine these three gas laws into the ideal gas law that we all know and love. The ideal gas law is stated PV is equal to nRT. P here is the pressure, V is the volume, little n is the number of moles, big R is the gas constant, and T is the temperature. The gas constant can be expressed in a couple of common different ways. One of them is that R is equal to 8.314 joules per mole Kelvin. This is all in SI units, which would mean that if you use this version of the gas constant, your pressure P has to be expressed in pascals, your volume V must be expressed in cubic meters, and your temperature T must be expressed in Kelvin. There's another form of the ideal gas law with a different gas constant, 0.08214 liters atmospheres per mole Kelvin. If you use that version of the gas constant, then you have to express your volume in liters, your pressure in atmospheres, and your temperature in Kelvin. Okay? So make sure that you've got the right units for the right job. So you can also express the ideal gas law as PV is equal to big N KT. If you do that, then big N here, of course, refers to the number of atoms or molecules of your gas, not moles. K is Boltzmann's constant, which is 1.38 times 10 to the minus 23 joules per Kelvin. Okay, so it's common to call P, V, and T the thermodynamic or state variables of the ideal gas, and then you couple that with either the number of molecules, big N, or the number of moles, little n, and put that into the ideal gas law. As I said before, be careful of your units. To emphasize how important this is, I'm going to do a simple little example problem. Solve for the volume of 1 mole of an ideal gas at standard temperature and pressure. Standard temperature and pressure, or STP, is at the freezing point of water and 1 atmosphere of pressure. So if you solve for the volume for 1 mole, then I rearrange my ideal gas law equation. V is equal to nRT over P. If I do that, N of course is 1 mole. First I'm going to use the gas constant R of 8.314 joules per mole Kelvin. The temperature at the freezing point of water is 273 Kelvin, and atmospheric pressure at sea level is 101,325 pascals. So plugging those numbers into that equation, I can solve for the volume, which is 0.0224 cubic meters. Now another way to express it is to get the volume in liters. In that case, N is equal to 1 mole again. The gas constant I'll use is 0.08214 liters atmospheres per mole Kelvin. The temperature T is 273, and then I divide that by the pressure expressed in atmospheres, not pascals, or 1 atmosphere. If I solve for that, then I get a volume of 22.4 liters. It's important to realize that when you plug temperatures into the ideal gas law, no matter what you're doing, those temperatures always have to be in Kelvin. For pressures, you might need to convert units, and some common conversions that you might see are that 1 atmosphere is equal to 101,325 pascals. You might also see pressure expressed in millimeters of mercury. In that case, 1 atmosphere is 760 millimeters of mercury. You might see it expressed in pounds per square inch, or psi. 1 atmosphere is 14.7 psi. And you might see it expressed in bar. 1 atmosphere is 1.01325 bar. So there's some common pressure units that you might see. There's a lot of them, and they can be a little confusing. Let me do another example problem before I leave you with this ideal gas law lecture. In this example problem, we have a tourist that's drinking some water. The tourist finishes their water bottle and caps that empty plastic bottle when they're sightseeing at Grandfather Mountain on a beautiful day with a temperature of 20 degrees C. Grandfather Mountain has an elevation of 5,945 feet at the peak where they are. So what that means is the atmospheric pressure is reduced from the pressure at sea level, and the atmospheric pressure is 81,370 Pascal. So what happens then is the tourists, after they finish their water and cap it, they hop in the car and drive down to their home, which is at sea level. When they get there, they notice that their bottle has been crushed by that change in pressure. How much smaller is the bottle at sea level? Okay, well, let's use our ideal gas law to solve for this. So if we assume that the temperature in the car doesn't change and the person inside the car keeps it at room temperature, which is about 20 degrees C, we also need to assume that they capped it nice and tight and the bottle didn't significantly leak. What that means is that if you look at the equation PV is equal to nRT, that N's going to stay a constant, T is going to stay a constant, of course R already is a constant. So what that means is that the products of the pressure and the volume, the initial product is going to equal to the final product because everything on the right hand side of that equation is a constant. So we can write P initial, V initial equals to P final, V final. I can then plug in for my pressures at the top of Grandfather Mountain and also at sea level. So 81,370 times V initial is equal to 101,325 times V final. I can then take my ratio of V initial over V final, and I see that that ratio is 81,370 divided by 101,325. When I solve for that, it gives me 0.803. What that means is that the bottle is only 80% of its initial volume when you get down to sea level. Okay, so the bottle gets crushed. And it gets crushed because it is flexible. Okay, the same thing wouldn't happen if you put it in a stainless steel water bottle because the steel is much stronger. And the pressure increases pretty dramatically going from a tall mountain down to sea level. All right. I hope that helps with some of your ideal gas law questions. If not, feel free to ask me and I'll see you in class.